Okay, let's look at theorem 2. It's called tangent theorem, right? So it states this. Line L is tangent to the circle centered at the O with radius R at point A. So A is a point of contact. If and only if the line has to be perpendicular to OA. OA is one of the radius, right? So let's try to prove that. First, we should probably draw a picture. All right, so you have a circle. All right, and the center is O, radius is R. All right, so L is the tangent, so line should look kind of like this. So it looks kind of like this. Right, so this is a line L. Right, then the point of contact would be here. This is A. Right. Right, so let's assume first assume that L is a tangent, so I'll just say L meets the circle O, R only at point of contact A. So there's only one point, right? So this is given, right? And 2. All right, so let's assume the opposite of what we want to say. So assume that say L, let's say, was not perpendicular to a radius at the point of contact. Right, so it's not, oh, that looks kind of bad. Right, so I'll say, right, not perpendicular, right, to the radius. Right, so let's say this is assumption for indirect proof. Right. So if this is not perpendicular, so let's see, I'm gonna just draw a picture here. So this radii is not perpendicular, right? So then we should be able to find a perpendicular. So we know that there exists a unique perpendicular. It looks kind of weird, but we should be able to draw a perpendicular to L, which so this is perpendicular 90 degrees and this is 90 degrees. So let's call this guy, say, M or something like that, right? So we know that 3, there exists M on the line L such that L is perpendicular to OM. Right. So this is the by existence of perpendicular from an exterior point. All right. Then what we can do is we can actually construct another point B, so on the opposite side from A. So we could probably put a point B here, right? Making sure that the length here is the same as length there. So AM and BM are equal to each other. So 4, we can construct, or there exists B in L such that, alright, so first condition would be it has to have the right between this condition. So it's opposite from A, so A and B. And also AM is equal to BM. Right, so this is by segment construction theorem. So I'll just say construction theorem. Right, then we can close it off to create a triangle. Right, so let's see, we know that 5, all right, OM is congruent to itself, OM, right? So this is by reflexivity. Right. Then we know that 6. We also know that the angle BMO, or actually maybe I should put the AMO first. AMO is congruent to angle BMO because they are those are the right angle, because let's see, L is perpendicular to OM, so I'm using number 3. All right, then we can establish the congruence between this right triangle there and that right triangle there. Right, we can probably use the side angle side. Right, so 7 side angle side, so triangle AOM or AMO, doesn't matter, AMO is congruent to triangle BMO by side angle side. Right, side is let's see, come from number 4, and angle is come from line 6, and another side is just coming from number 5. Right, so we have that, and which means that OB and OA are equal to each other. So 8 OA and OB are equal to each other, and this is equal to the radius. So this is by corresponding parts of congruent figures. Right, then we notice that since OB is equal to R, so 9, all right, L actually meet the circle at B also. L also meets the circle at B, right? Which is a contradiction, because L only can meet at A because it's tangent, so it contradicts line number 1, and it comes from the fact that the OB is equal to R and B is on the line, so it's, maybe I should say, line 4 combined with line 8. Right, so line 10, right, therefore, right, so we know that let's see, so assumption here is wrong. L is actually has to be perpendicular to OA. Right, so this is a rule of elimination. Right, so this will complete the proof of the this implication. Right, so let's try to prove the other implication.